Hello and welcome to Sam Biology class. Friends, today we shall discuss about the principle and the applications of gel filtration chromatography. Before that, I request all of my friends, please subscribe my YouTube channel. Gel filtration chromatography is a powerful technique that separates molecules on the basis of their size and shape. It exploits the molecular sieving properties of a variety of porous materials. This technique has widespread applications and many advantages, such as gentleness of the technique, thereby permitting the separation of a labile molecular species, excellent reproducibility, almost 100% solute recovery, comparatively short time and relatively inexpensive equipment required for its operation. Gel filtration chromatography is carried out in either column mode or thin layer mode. It is also known as the molecular sieve or molecular exclusion chromatography or gel formation chromatography. Like other chromatographic techniques, gel filtration also involves two immiscible phases. One is the stationary phase, one is the stationary phase, and the other is the mobile phase, and the other is the mobile phase. The stationary phase is composed of suitable gel beads. The stationary phase is composed of suitable gel beads or porous glass granules or porous glass granules. The gel beads are made up of polymers such as dextran, cross-linked dextran, cross-linked dextran, agarose, polyacrylamide, or polyvinyl chloride or polyvinyl chloride. The mobile phase is a suitable solvent. The mobile phase is a suitable solvent. This figure shows the principle of molecular sieve in column mode. It is very simple. A column packed with suitable gel beads or porous glass granules is allowed to attain equilibrium with a solvent which is suitable for the molecules to be separated. This is the column which is packed with suitable gel beads. These are the gel beads which are porous. This figure shows the cross section of a single gel bead. These are the gel pores and the bead is surrounded by molecules of different size. Only the molecules which are smaller than the pore diameter will penetrate into the gel pores and will move through the channels. Because of this, small molecules will take comparatively more time to come out of the column. whereas large molecules will not be able to enter into the gel pores and they will pass down the column directly through the interstitial spaces between the gel beads. Large molecules thus move with little resistance. When a mixture containing molecules of different size is applied at the top of the column, large molecules will pass down the column directly through the interstitial spaces between the gel beads. This is because gel pores have a smaller diameter than what is needed for the large molecules to enter into the gel pores. These molecules thus pass down the column with little resistance. Small molecules, on the other hand, will penetrate into the gel pores and will move through the channels. After coming out, these molecules penetrate into the nearby gel beads. Due to this movement from one gel bead to another through these microscopic channels, small molecules will take more time to come out of the column. These molecules are thus said to be retarded, and the degree of retardation of a molecule is proportional to the time it spent inside the gel pores, which is a function of the molecular size and the pore diameter. For a gel, the exclusion limit is defined as the molecular weight of the smallest molecule incapable of entering the gel pores. For a given gel, the distribution of a molecule between the outer solvent and the inner solvent is defined by distribution coefficient Kd, which is a function of the molecular size. The solvent which is present outside the gel beads in the interstitial space is called the outer solvent, and the solvent which is present inside the gel particles is the inner solvent. For large molecules which do not penetrate into the gel pores, distribution coefficient is equal to 0. For small molecules which enter into the gel pores and diffuse into the inner solvent, the distribution coefficient is equal to 1. Due to the variations in pore size for a given gel, some of the inner solvent will be available and remaining will not be available to the molecules of intermediate size. In this case, the distribution coefficient will vary between 0 and 1. This molecular dimension dependent variation of the distribution coefficient between 0 and 1 makes it possible to separate molecules within a narrow molecular size range on a given gel. Now let us discuss as how gel filtration chromatography is used for the determination of relative molecular weight. This equation represents the mathematical relationship between the void volume VO, the volume of the inner solvent VI, the distribution coefficient Kd and the effluent volume VE. The volume of the solvent surrounding the gel beads is the void volume, and the total volume of the solvent that has passed through the column when a substance appears in the effluent is known as the effluent volume. Out of these variables, distribution coefficient is the characteristic of a given molecule being separated. It is not dependent on the geometry of the gel bed, but the effluent volume is dependent on the size of the column where separation is being carried out. Out of this, the volume of the inert solvent Vi can be calculated if we know the dry weight of the gel being employed and its water regain value. This is the equation where A is the dry weight of the gel and Wr is the water regain value. Two different substances having different molecular weights and therefore different distribution coefficients Kd1 and Kd2, the difference in the effluent volume V1 minus V2 is given by this equation where Vs is the volume of the sample that should be applied for the complete separation of two different substances. The distribution coefficient and the effluent volume are both related to the molecular size. Therefore, one can calculate the relative molecular weight of various biomolecules if their effluent volume is determined by gel filtration. Gel filtration chromatography has many applications. Number 1, purification of biomolecules. Viruses, enzymes, antibodies, hormones, nucleic acids and even polysaccharides have been purified by gel filtration. Number 2, one of the most important applications is the determination of relative molecular weight of various biomolecules. Number 3 is desalting. And finally, a dilute solution of macromolecules whose molecular weight is greater than the exclusional limit can be readily concentrated by utilizing the hygroscopic nature of the dry gels. Friends, this is all about the principle and applications of gel filtration chromatography. For more updates, subscribe my YouTube channel, Sam Biology Class.